Welcome to our final lecture, Lecture 18. This is the second half of the Cosmos and Is There Life lecture. So without further ado, let's get into it.
This is the part of the lecture that everybody's probably been looking forward to the entire semester. Is there life? I don't know if you've noticed this yet, but humans like to make ourselves the center of attention. At one point, we were the center of the universe, but with a more human-centered viewpoint, there have been 7 major phases in the history of the universe that we have identified. The particulate phase, galactic phase, stellar phase, planetary phase, chemical phase, biological phase, and then our own cultural evolution. Together, these evolutionary changes, or stages, make up the grand sweep of the cosmic evolution, which is the continuous transformation of matter and energy that has led to the appearance of life and civilization on Earth. Were these events random? Or were they in some sense natural? So this is the question I want you to think of for the rest of this lecture. Are we unique? Or is this a technologized civilization that's inevitable? Are we alone? Or one of many civilizations? And whichever answer you come to, it should scare you. You should be scared by either answer. It should be sad to you if we are alone, because that means that we will be spending our entire lives and of Earth, the Earth, human livelihood, searching for other life, expanding, hoping, and we'll find nothing. And that itself is like saying you're the last human alive, but you've been looking for another human to talk to. And then, is it inevitable? Are we one of many? That should also scare you. Because just look at human history. We responded to finding new groups of people by either enslaving them, killing them, or deciding that we need to take care of them because they're inferior. And if people on our own planet thought that way, don't you think other groups of life would think that way? Is it possible that there's a group out there that would rather destroy us all and be the only civilization in the universe? Or in the case of Jupiter ascending, we're just a food group. Wouldn't that scare you? It should. Scientists regard the following as characteristics of living organisms. 1. They can react to their environment and can heal themselves when damaged. 2. They can grow by taking in nourishment from their surroundings. 3. They can reproduce, passing on their genes. If you do not have a pair of genes, you need to talk to your parents about passing on their genes because you need some. They have the capacity for genetic change and can evolve to adapt to changing environments. These rules are not one and done. There are other objects in our universe that exhibit some of these characteristics but are not technically alive. Researchers think that the distinction between living and non-living is more one of structure and complexity than a solid rule. A good definition of life isn't quite grasped yet. So I want you to think right now, what are some other things that, based on these characteristics, could make it living? Here's an example. Stars. They react to the gravity of their neighbors. They grow by accretion. They generate energy and reproduce by triggering star formation. But they aren't alive. Another one that many of you probably have immediately thought of was viruses. They react to their environment and heal themselves when damaged. They can grow taking in the nourishment from your body and your cells. They can reproduce, and they do so, making your cells explode with mini virus babies. And they have the capacity for genetic change. Take a look at the flu vaccine. They have to change it every year because there's a new strain of flu. It evolves. It adapts. Bacteria adapts, but we know that's alive, and we know viruses aren't, right? What about a true AI or android? It can technically exhibit all of these factors as well. And it poses the question, is an AI alive though? The question that have become many movies. From this, extraterrestrial life is summed up by the assumptions of mediocrity. Because life on Earth depends on just a few basic molecules, therefore all life should depend on a few basic molecules. And because the elements that make up these molecules are all from stars, everything else should be made up from molecules that are made from stars. The law of science that we know applies to the entire universe. So given a good amount of time, there must be life elsewhere. Right? What do we know about early Earth? You know about protoplanet Earth when stuff started to actually form ground? Not much. The geologic record tells us that Earth was once molten and that there was a lot of impacts, like protoplanets and hitting us, asteroids, comets, chunks of stuff. And we think that a combination of these impacts and outgassing from the many volcanoes that formed our atmosphere and eventually gave us water. So early Earth was home to many, many shallow seas at one point. Sea level was much higher at this point because we didn't have ice caps yet. Why? I don't know, because maybe we were just super duper hot. Land masses are still forming from volcanoes. Tectonics are just beginning. Over time, the land masses did become more prominent as sea level dropped. And then guess what? Ice caps started to form. We start to see land masses similar to Pangaea, breaking apart and coming back together, breaking apart and coming back together over the millions and millions of years that we've been around. But before the atmosphere really formed, not only were we volcanically active, there was a lot of UV and other radiation bombardment on the planet. No atmosphere means no protection. It did provide a lot of energy combined with these impacts, natural radioactivity and lightning. This formed the ammonia, methane, and carbon dioxide and water that we had on early Earth. The thinner atmosphere, into amino acids and nucleotide bases, for organic carbon-based molecules seen as the building blocks of life. Amino acids build proteins, which control our metabolism. Nucleotides are what makes our genes. Anyway, we have these lovely things. We aren't really sure how that happened. When did that start to form? What we do know is that at some point, single-celled organisms formed in those shallow seas, which we called prokaryotes. Eventually, they evolved into bacteria, or eukaryotes, and multicellular organisms. Eventually, that evolution track got us organisms like us, and dolphins, the only other truly intelligent being on the planet, and they will eventually thank us for all the fish. This experiment has been reproduced many times with the outcome, which is the Urey-Miller experiment, the creation of the primordial soup. It was first conducted in 1953. Harold Urey and Stanley Miller created a mixture of materials thought to be present on Earth a long time ago, known as the primordial soup. They made it of water, methane, ammonia, and carbon dioxide. This is not a soup I recommend eating or drinking. Probably not that good for you. They sparked it with electricity, and a few days later they checked on the mixture, and they found amino acids like what we have on Earth had formed, and nucleotide bases. And this demonstrated that biological molecules can be synthesized from non-biological means. But never has this led to any form of life being formed. More recently, scientists began to ponder if these amino acids came from outside our planet, from impacts. Why? Because there may not have been a sufficient amount of energy in Earth's young atmosphere to power these chemical reactions, let alone lightning, and there may not have been enough materials. NASA researchers conducted their own version of the Urey-Miller experiment, exposing an icy mix of water, methanol, ammonia, and carbon monoxide, which we find in interstellar grains, to ultraviolet radiation to stimulate energy from a nearby newborn star. They found it formed droplets surrounded by membranes containing complex organic molecules. No amino acids, proteins, or DNA were found. But the results show that even in the harshness of space, the vacuum that is the void, the formation of complex molecules and primitive cellular structures are possible. The movie Evolution is a good reference for this in the sci-fi realm. So if you haven't seen that, I recommend watching it. The interstellar molecular clouds are known to contain many complex molecules and large amounts of organic material, and this was detected on Halley's Comet and the Hale-Bopp Comet. This means that comets that may have hit early Earth may also have had a complex molecule or molecules that they brought with them. In addition, a meteorite found in Murchison, Australia in 1969, soon after its impact, contained 12 of the necessary amino acids to produce life on Earth, suggesting that complex molecules necessary for life could in fact come from space. And recent work by Dr. Chris Mehta and Dr. Pasek have furthered this research, stating that the meteorites or comets carrying amino acids would only be able to survive in certain atmospheric conditions. meaning amino acid bearing impacts would not have occurred when scientists think they may have, or the conditions they thought. Now let's try to put a timeline here. Fossil evidence puts the first once called organism, an algae, at 3.5 billion years ago. Multicellular organisms didn't appear until about 1 billion years ago. We know Earth has been around for about 4.6 billion years. That means for about 1.5 billion years, we don't really know what happened. And it's at this point where we had a very molten Earth, and there isn't really much for us to go on. We have some very old grains of zircon, because zircons never melt. Once they form, they're formed. And that's how we were able to assume the age of the Earth. But we don't really have any idea what was happening there. There's no fossil evidence before that, because they didn't exist. But now let's say we take this and we put our historical perspective into 46 years rather than 4.6 billion years. Ready? Life originated 35 years ago. Earth was about 10. 6 years ago, abundant life flourished. 2 years ago, plants and animals dominated the land. Dinosaurs reached their peak a year ago, and then they suddenly died 4 months later, and we are still missing them. Human-like apes became ape-like humans last week, and the most recent ice age was 4 days ago. Homo sapiens emerged 4 hours ago. We are very young. We're 4 hours old, and agriculture was invented about an hour ago. And the Renaissance and modern science occurred in the last 3 minutes. So as you can see from this analogy, we aren't that significant in our own time scale. Life takes a long time to really get going. We have similar events happening elsewhere in our solar system, don't we? Life as we know it tends to mean carbon-based organisms that originated in water-like environments. What about on other planets or other planetoid bodies? What about if they have other types of organisms, like silica-based? What about other areas in our solar system, like the moon or Mercury? Well, they don't have an atmosphere or magnetic fields, and it's a tad too violent there, radioactive and impact-wise, for life, so no. The Jovian planets? No, we don't really know of a solid surface there, so probably no. What about the moons? Most have frozen surfaces. We can't rule life not existing on more hostile environments like Titan or Europa. We constantly find organisms living in areas on our own planet previously thought to be extremely inhospitable, like black smokers on the ocean floor or sulfur-rich hot springs of Yellowstone. And we call these organisms extremophiles. Europa, Ganymede, Titan, Enceladus are all frozen. But there's probably liquid under those surfaces, and they may harbor life under the ice. Which, by the way, was a B-rated movie up on Netflix. You can probably find it. Mars? Maybe. Maybe Mars once harbored life, or the beginnings of it. How? Well, we know Mars once had a thicker atmosphere. I mean, it's gone mostly now, but we know it existed. So maybe once upon a time, life did start there. Maybe. You have yet to find any evidence of life on Mars. Not for lack of trying, but we never actually sent any missions to the more interesting parts of the planet to test, like the poles where there's actually water. The most recent mission was the Mars Phoenix, and unfortunately that mission wasn't equipped to find life like previous missions were, which we sent to the safer parts of the planet because, I don't know, these things are expensive. They did find evidence of water in the soil near that caps, though, and the chemical composition of the soil there was much more Earth-like than we expected. And this means Martian microbes may have been capable of digesting oxygen-rich compounds in the Martian soil. Recently, and this has still not been actually put out, last I checked, fossilized bacteria had been found on meteorites originating on Mars, or what they think is bacteria. The last time I checked to see if they had put out a paper on it, it was still being researched and identified. But if there was fossilized bacteria on Mars, either it's from Mars or from somewhere else. And either way, that would be amazing. Can you imagine if we found bacteria coming from somewhere? And if it originated from Mars, like that bacteria was fossilized onto a meteorite that impacted there, or that meteorite came from somewhere else where bacteria was forming. Like, think about how cool that would be. It would also be kind of frightening. Now this brings up the other question. How likely is it that life in any form exists in the universe? To do this, we use the Drake equation, which was made by Frank Drake to calculate the number of technological intelligent civs in the galaxy. He made this over a lunch conversation, by the way. There's a video you can watch on YouTube about it that's kind of funny. Several of the factors of the equation are largely a matter of opinion, so we don't actually have enough info to accurately determine all of them, so we can't give us an ice hard number like scientists love. But basically, it's made up of this. The rate of star formation averaged over the lifetime of the galaxy, multiplied by the fraction of stars having planetary systems, multiplied by the average number of habitable planets within those planetary systems, multiplied by the fraction of those habitable planets on which life arises, multiplied by the fraction of those life-bearing planets in which intelligence evolves, again multiplied by the fraction of those intelligent planets that become like us with technological society, and then the average lifetime of a technologically competent civilization will equal the number of tech intelligent civs now present in the galaxy. Complicated. Right? But it makes sense. That's essentially what should happen. Let's try to figure it out ourselves. Rate of star formation. In our galaxy, about 100 billion stars now shine. The estimation is that there is a formation of 10 stars per year. Maybe an overestimation, as astronomers think that fewer stars are forming now than in earlier periods due to a lack of stellar dust, but we're just going to say 10. What about the fraction of stars with planets? Big question. In previous lectures, we have talked about searching for exoplanets in one of our earlier ones. We found quite a few stars with Jovian-like planets orbiting them, and recent information suggests that more stars should have planets than originally expected. With terrestrial-like planets, we're not sure, although we think more should exist. Now, only 10% of surveyed star systems near us have planets that we can detect with our current technology, but because of the condensation theory, astronomers think it is more likely that all stars have some sort of planetary system. So we're going to give a factor of 1 for this value. What about the number of habitable planets? What is the likelihood of a planet being able to harbor life? Ha ha! Well, temperature is one of the most important factors in this case. Although catastrophic events like supernova or impacts can also be very important. You don't want to be next to a supernova, you're dead. So surface temperature of a planet depends on 2 things. Thickness of its atmosphere, if we're thinking Venus versus Earth versus Mars, and its distance from its star. This is a 3D stellar habitable zone of comfortable temperatures around every star type. So if we were to look at an M-type star, it's much bigger versus a 1-type star and a 0.5 molar star, basically low mass stars versus high mass stars. Sun-like stars surrounded by a relatively huge habitable zone because liquid water may exist on a planet's surface at multiple different distances. But location is very important. Habitable zone is the range of distances within a planet of mass and composition, similar to Earth, would have a surface temperature between freezing and boiling points of water. Basically, if you're too close, your water's boiling. If you're too far, your water's freezing. You have to find that Goldilocks zone. Get it? So ideally, if we were to switch Mars and Venus, Mars would be habitable, and possibly so would Venus, because its atmosphere is so thick, being a little bit farther from Earth or from the sun to where Mars was might make it a habitable area, just as Mars being just a little bit closer than Earth, basically where Venus was, with the thickness of its atmosphere might make it habitable as well. So here we have G, F, and M stars. O and B class stars would burn out too fast. A and F stars would have very large habitable zones, with G, K, and M having successively smaller ones. The habitable zone is the range of distances from a planet to its star. It has to have a mass and composition similar to Earth in this case. Remember, we want a Goldilocks planet. And would have to surface temperatures between freezing and boiling points. So in our habitable zone, we have Venus, Earth, and Mars. Okay, and like I said, if we swapped Venus and Mars, theoretically, we might be able to live on them. We also have the habitable planets helping stabilize and protect, or we have the Jovian planets helping stabilize and protect these habitable planets because they are outside of us, helping protect us from things coming inwards. Another external force that affects a planet's habitability is the galactic habitable zone. Where you're located in the galaxy is very important. 2 lectures ago, we talked about black holes at the center of the universe, and how being in the galactic center would not be a great place to live on a planet because it would be very dangerous for you as a human or other being. There may be, in fact, galactic habitable zones where if a star is outside of it, conditions are unfavorable, but being too close to the galactic center also makes it unfavorable. Insufficient heavy elements to form terrestrial planets or populate them with civilizations would occur because the galactic center, star formation is low, and a few cycles of star formation have occurred. Whereas if you're too far away, there's no new stars forming. You come too close, you have all this radiation, you have supernova. It's just crazy. Effects of nearby stars also send comets from Oort clouds to the inner regions. So if you have too many stars close to you, it could cause a lot of impacts on your planets, preventing life from forming. To estimate the number of habitable planets per planetary system, must look at how many of each type of star shines in the galaxy habitable zone. A few percent of the known planetary systems contain habitable planets. Potentially habitable moons make this number higher. So with uncertainties, a value of 1/10 for this factor is what we are giving for this equation, because you only have a few percent of the known planetary system. Now that we're past that more complicated part, the fraction of habitable planets with life. This is a big one. The number of possible combinations of atoms is huge. If the reactions that led to life on Earth were random, who knows if it would ever happen again. The evidence suggests that certain chemical combinations are strongly favored in nature over others, meaning they aren't actually quite random. There are 1,500 combinations preferred by nature, and they are made from about 50 simple building blocks. So we're going to give this value a 1. Now we're looking for a fraction of planets with life that has intelligent life. As with evolution of life, is the appearance of well-developed brain unlikely or likely? One school of thought maintains that given enough time, intelligence is inevitable, as natural selection has always appeared to prefer intelligence. So at least one organism on a planet will always rise to the level of intelligent life, right? So we're going to be optimistic. Give it a value of 1. Others argue that we are the only known case of intelligence. For 2.5 billion years, life remained simple and dumb, but it survived. However, optimism goes to 1. Why do we know that intelligence arises, and how do we even know that technology is going to become a big factor? This is the 6th problem. The fraction of planets where intelligent life forms and uses technology. We are estimating if intelligence will inevitably create technology. Again, 2 views. Technology isn't inevitable. It can be avoided. Take a look at the dolphins. Super intelligent. No technology. Unless they're hiding Atlantis from us, in which case we have to talk. And this makes the value less than 1. If technology is inevitable, this makes the value close to 1. G number 2 is the most probable to us, not just because scientists are super optimistic opals, but because there are many civilizations on Earth independent of each other that used tools and other more advanced technology. Take a look at the Mayans, the Egyptians, the Mesopotamians, Indians, China. None of them interacted, but they created all this technology that they used to build their empires and their civilizations that survived for hundreds of years, thousands even. So we're going to be optimistic and say we're going to put the value at 1. And here's the final factor in the Drake equation, and the most widely unknown. We are the only major planetary civilization that we know of, and we have not died yet. So we don't really make good source material. Instead, we're going to do something else. We're going to combine all the other 6 factors. Right now, the first 6 factors, as we assign them, is 10 times 1 times 1 times 1 times 1 times 1, which is 1. Therefore, the number of technological intelligent civilizations now present in the Milky Way galaxy is equal to the average lifetime of a technologically competent civilization in years. Sounds nice, right? Well, this means if the average lifespan of a technologically advanced civilization is 1,000 years, then there are 1,000 civilizations in the galaxy. If there are 1 million years, then 1 million civilizations, etc. But if time is short, then there are indeed fewer civilizations, and they would be far between. It also means our communications would probably never reach each other before we died out completely. So again, if it's a short time, we're never going to reach anybody. But let's be optimistic here. Let's assume that the lifetime of technology advanced civilizations is 1 million years, meaning there would be about 1 million civilizations, roughly 30 parsecs or 100 light years from each other in our galaxy. All right, cool. That means two-way communications would take at least 200 years. And though we would want to visit them at our current technological level, this would be not very pragmatic. The journey itself would take 1 million years, meaning we would get there right as both of our civilizations just died. Well, two-way communication, 200 years each way. That would be kind of a fun way to play phone tag. Hi, we are Earth. We have all this cool stuff. Look at our iPhone. 200 years later, we get something. Oh, blah, blah, blah. What do you mean you only have this very strange, very limited technology? Oh no, we far surpassed that. About 200 years ago, we moved forward and this happened. And you realize that we would basically seem like we were from the 1920s to them. And then they would appear to be from the 1920s to us. Because we would be jumping in technology. That would make what we had previously just from 1990 to 2020. Think about the computers that we had in 1990 versus now. Like, we would be like, whoa, dude, that computer is so old, I can't deal with the dial-up. And that person from 1990 coming to 2020 and seeing our computers now would be like, oh my god, it's so fast. Okay? So, it wouldn't work. Well, in our own search for possible life, we did launch probes. We have the Pioneer 10 in the 1970s, which is now well beyond Pluto on its way out of our solar system. Contains data about our civilization, mostly in the universal language of math. We think it's universal. Because, of course, if you don't understand math, you can't be an intelligent life form. And then in 1978, we launched another interstellar probe with much of the same information called Voyager. Despite this, we don't really have a way to know if they're ever going to find life. We have no way to communicate with Pioneer 10 or Voyager. Oh well, someone will find them, and they'll be like, hey cool, I wonder what this cassette tape is, and what it is, and why does it keep talking in weird ways? What are all these different voices coming from it? Because we have them playing information from RTVs, from speeches, and it's cool. A much more practical way of communicating is using electromagnetic radiation, like radio. Radio band doesn't get impeded by the dust and gas or other material in space, making it an ideal communication tool. Because we can't possibly broadcast to all stars at once, we simply listen. We listen for communications from other civs, like weird stalkers. This raises a question or two. Which direction do we point our radio telescopes? Are other civs even transmitting communications on that band? If they are, how do we know it's them and not something that forms naturally in space? Think about Earth. We give off a lot of radio waves. Surprise! Spinning Earth would emit bright flashes of radio radiation every few hours as the most technological regions of our planet rises and sets. Earth is a more intense radio wave emitter than our own sun is now. If any sufficiently advanced civilization resides within 20 pascals, 70 light years from us, they would have noticed us by now. But it's very plausible, like Bill Nye has pointed out, that other civs may not be communicating on the radio wave spectra. Why? Because maybe they've figured out an advanced communication on other wavelengths. Basically, they're using fiber optic cable internet and we're still using copper wire. The other thing is that because of finding these advanced forms of communication, that all radio emission ceases, and that the lack thereof maybe indicates intelligence. Maybe they're ignoring us because we are still giving it off. But we're going to assume, we're going to be pragmatic here. We're going to be hopeful, very hopeful. Optimistic opals. That's what we are. We're going to assume other civs do the same thing as us. They are actually communicating using radio waves. Well, what frequency would they be relaying on? The questions. Some arguments suggest that civilizations might communicate at wavelengths around 20 centimeters in length. So remember, hydrogen atoms gives off the 21 centimeter wavelength. Hydroxyl, or OH, one of the most simplest molecules, also radiates near 18 centimeters. Those two together, H and hydroxyl, form water, being that water is a arguably major evolution medium for all life, and radio radiation travels through the disk of our galaxy with the least disruption. Researchers have determined that the 18 to 21 centimeter range is probably the best wavelength range for civilizations to communicate, and therefore we call it the water hole. This radio interval might serve as an oasis where all advanced galactic civilizations can gather to conduct their electromagnetic business. Welcome to the water hole. The 18 to 21 centimeter range also lies within the quietest part of the spectrum, the least amount of interference or static from stars and interstellar clouds. Atmospheres of typical planets also interfere less at this wavelength, and a few radio searches are in progress at frequencies and around the water hole. Please enjoy your stay, and please use our technology carefully. The water hole. A new day. Sounds like a weird thing you would hear on some sci-fi movie, right? Right. It exists. It is a thing. We do actually do that, and there is an institute known as the SETI Institute, or the Search for Extraterrestrial Intelligence, SETI. This is a real thing. It's not something where it looks like a bunch of alien chasers, people who sit around in campers with tinfoil on their heads. This is a real group. It is a real institute looking for extraterrestrial life, looking for life outside our planet. They get funding. They are a real thing, and it is super cool. You can go to their website and read all about them and see what they're doing. But they have an Allen telescope array, and they work with listening. They listen all the time, and it is quite cool. All right, now, we've been doing all this stuff. We have the SETI Institute. We have everything. Why haven't we found or seen any signs of life? This is the Fermi paradox. We haven't seen anyone yet, but supposedly there should be many intelligent life forms in the galaxy, just based off of the Drake equation. The Milky Way contains hundreds of billions of stars, and billions of them are similar to the Sun, meaning it's likely that some of these stars have planets that are Earth-like. And if we assume, via the Copernican principle, that Earth is not particularly special, then intelligent life should also exist in some fraction of these Earth-like planets and other places. Some of these intelligent life forms might develop advanced technology and even interstellar travel. Heck, if they've been around longer than us, they should be having interstellar travel, right? Plenty of time. So why haven't we seen anyone? Where is everyone? Are we alone? The SETI Institute actually dedicates all their time and energy to listening to radio radiation in hopes of finding signs of life outside our solar system. And so far, they haven't heard anything yet. This leads us to the Kardashev scale, where we have 3 types of civilization, types 1, 2, and 3. The type 1 civilization has the ability to use all of the energy on their planet. We are not quite a type 1 civilization yet, but we're close. Carl Sagan created a formula for this scale, which puts us at a type 0.7 civilization. We're close, but we're not there yet. A type 2 civilization can harness all of the energy of their host star, and the theories of how to do that is quite interesting. I totally encourage you. We're not going to cover it in here. Go watch some YouTube videos. They are fantastic. Type 3 civilization blows the other 2 away. At this point, your civilization can access the power comparable to that of the entire Milky Way galaxy. Imagine having that level of power accessible to you. Think of everything you can do, the interstellar travel, the type of information you'd be able to gather from other planets, going out and researching. Like, it would be so cool. There are many movies that take place out in the center of space. Star Wars would be a type 2 civilization. They can harness the energy of a star. They might even be a type 3 civilization. You have many, many movies where we're dealing with many civilizations coming together and dealing with each other, being type 2 or type 3 civilizations, having massive amounts of power. Take a look at Guardians of the Galaxy. Look at all the civilizations they come into contact with. How many of them are type 2 or type 3? We still haven't seen any other life. The Great Filter is one of the reasons that we have come up with. Is that there aren't higher life forms. It's the idea that a planet with a civilization, in order to do intergalactic travel, would need to get to a Type 3 civilization. Maybe there aren't any yet. And this might be because of the Great Filter, which is a series of hurdles that a species must overcome in order to evolve. And from this point, it gets kind of scary. This means we have either passed the hurdle, yay! Or we still have to pass the major hurdle, and we are screwed. We are the first to make it past the hurdle. Oh, that would be nice. Also scary. The other civilizations made it and then killed themselves off first before we could find them. Ha! Another theory is that there is intelligent life beyond our own, but they haven't interacted with us yet. In which case, they may be zookeepers. Fun fact, we are actually being observed for anthropological reasons, and there is a intergalactic zookeeper association that keeps planets where Type 1 and below civilizations are watched and observed to see how evolution and in the form of technology occurs, right? What better way to study how an intelligent civilization forms than to watch one? Star Trek, great example. The Vulcans watched humans on Earth, but once they reached a specific technological advancement, they revealed themselves to us and gave us the technology we needed to travel the galaxy. Another thing they're staying away from us is because we breathe oxygen. Oxygen is an oxidizer. Ha. We are slowly oxidizing ourselves, which means we are slowly burning ourselves. Which is why eating antioxidants is a good thing. And so to an outsider, we breathe fire. And you do not mess with death breathers. Another thing, we're too primitive. We can't pick up on their signals yet. So they're just ignoring us. We're not important because we haven't reached the same kind of level they're at. So why should they bother to talk to an ant? Have you tried talking to an ant? They don't respond well, do they? Another thing is, we just live in the sticks. Nobody comes out here. We are super country. Nobody's going to come out here because nobody cares. Colonization is hysterical to higher civilizations. They're much happier staying on their own planets or in their own solar systems where nothing else is living and just living there. And colonizing other planets is not necessarily something interesting to them. Or there is a predatory civilization that is killing off everything else, in which case we should shut up before they find us. Another civilization did visit here, but before we formed and they moved on. Or we're food. Or for energy, but don't know it, like Jupiter ascending. Either way, this slide are two videos that I encourage you to watch. They are both about the Fermi paradox. You have part 1 and part 2. If you have not watched it yet, or you have watched it yet, go ahead and watch it again. This guy's pretty good. And there's other videos out on YouTube that explain the Fermi paradox as well, as to why we haven't found any other aliens, etc. I hope you enjoyed our final lecture, and I hope it's made you think about what is out there versus just what's underneath your feet.
Thank you so much for taking my class. I hope you enjoyed it.